In this experiment, we'll start with the next experiment of digital electronics, that is the use of a synchronous counter. The aim of this experiment will be to design a mod 4 synchronous counter. The mod 4 here implies that the counter will start counting from 0 and will go up to 3, and synchronous implies that the flip-flops that we'll be using for counting will operate on a common clock. So a counter is a very simple device used in digital circuits that is used for counting, and we use it with a clock which acts as a trigger. The apparatus that we require is the baseboard, a couple of ICs, and a jumper wire. The IC that we'll be using over here, that is 7473, is the JK flip-flop IC, and we'll also require the use of an XOR gate, that is IC 7486. The procedure is quite similar to the ones that we followed in previous experiments. We'll have to mount the IC in any one of the 10-pin sockets available on the board, and using the provided pin diagram you can make the necessary connections, starting from VCC and ground to plus 5 volts and to the ground pins, and you can connect the input pins to plus 5 volts, and you can connect the output pins to the LED box. Since this is a mod 4 counter and we'll be counting from 0 to 3, so in binary that will require 2 bits. That is why we'll also have 2 output pins which both will be connected on the LED box. Thus we can verify that the counting is happening correctly. So according to the pin diagram we can see over here, you will have to connect 2 pins, that is pin 1 and pin 5, to the clock that is provided on the board, and you will have to connect pin 2 and pin 6, that is the clear bar pins, to positive 5 or plus 5 volts or to logic 1. And the output can be observed over here for this flip-flop from Q, and for the second one at pin 9, and Q bar is basically the complement of the output. So since we have two outputs, since we have two JK flip-flops, we can say that one of them will give us the MSB or the most significant bit, and the other one will give us the LSB or the least significant bit. So from this diagram we can see that the JK flip-flop on the right gives us the LSB, and on the left it gives us the MSB. So for the LSB JK flip-flop, both the inputs of J and K are connected to logic 1, and the output of this flip-flop goes as an input to the MSB flip-flop, and will also require the use of an XOR gate over here. And both of them are operated with a common clock. Once these connections are made, you can power on the board and you'll see that automatically the counter starts counting from 0 to 3. You can verify this by by seeing the changes happening in binary for every decimal number. And so in the next part of the video, we'll demonstrate how you can implement this circuit on the mobile lab, and also how you can obtain the output and verify it.
You can refer the lab manual for pin diagram and make the valid connections. So at first we will connect the VCC and ground of both the ICs. So for 7473, the pin number 4 is VCC and pin number 11 is ground. Whereas for XOR gate, the pin number 14 is VCC and pin number 7 is ground. For JK flip-flop, the first pin is the clock. We will connect it. The pin number 2 is clear bar, so it must be connected to the VCC or plus 5 volts. Then for second JK flip-flop, the pin number 5 is clock. So it can be shorted with the clock of first IC, which is pin number 1. After that, pin number 6 is the clear bar for second for second JK flip-flop. So again it must be connected to the plus 5 volts. And then the input of second JK flip-flop must be connected to the plus 5 volt. So it is the pin number 7 and pin number 10. The input of first JK flip-flop is shorted, so pin number 14 and pin number 3 are shorted. And the input given here is output of XNOR gate. It's here. The output can be observed on Q1 and Q2, which is pin number 12. It was Q1 and pin number 9, which is Q2. And again Q2 is the input of our XOR gate. And the second input of XOR gate must be ground. So here we complete our connections. Now let us check the output. So here we can see that the output is starting from 0 and going to 3. So 0, then 1, 2 and 3. So all the output is in binary. So yeah, that's it. Thank you.